Hola chicos. Recibí un regalo de mi mamá. Es una camiseta nueva, Forged in Fire, t-shirt. Me encanta. Ayer mi gato encontra un otro gato y ellos estaban jugando. Estaba muy lindo. Ahora yo espero los otros estudiantes. No hay muchos estudiantes aquí. Por lo tanto, yo voy a practicar mi español. Ayer yo encontré un podcast, se llama Conversaciones en Español, y es muy bueno porque ellos hablan muy despacio y muy claramente, y ellos usan las palabras que yo aprendo en mi clase de español. Me encanta lo. Ok, vamos a empezar. Okay, let's see. So this is AP Physics 1, 2, 26. Periodo 6. So today, what we are going to talk about something called wave superposition. Okay. And so what wave superposition is it is when two or more waves combine. Okay. So like for example, if you look at the surface of the ocean looks really complicated. Okay, it has lots of peaks and valleys, and it's changing all the time. And what we're seeing is not the individual waves that are traveling through the ocean. What we see is the combination of all of those waves. The superposition of all of those waves is making the really complicated surface that we see. Okay? So that is what wave superposition is. It's when we're combining waves. What if you're at a party and the party is very loud because everyone is talking and there's music playing and so on? Um, you know, that is a superposition of sound waves. All of those sound waves are passing through each other and combining to make bigger waves or smaller waves. If you're in a room and that room has multiple light sources, then the light waves are superposing. Okay? So all that superposition of waves is happening all the time, and it just means when waves are combining. Okay? So there's a couple of ways that waves can superpose. And one thing I want to say really quickly is it's not superimpose, it's superpose. Okay? Not superimposition, it's superposition. So what if I have two waves, and this wave is a peak, and this wave is a peak, and these two waves are on a collision course. What is going to happen when these two waves overlap with each other? Well, what we would do is we would take the height of this wave and we would take the height of this wave, and when they overlap, we would just add the two heights together. So the resultant wave is going to be something like this tall. So it's going to do something like this. Okay? And so when that happens, that is called constructive interference. Okay? So constructive interference is when waves combine to make a bigger wave. All right? So, yeah. So in this case, these two waves combined, the waves got bigger. An important point is that it doesn't have to be peaks. Two valleys can also combine to make a bigger valley. So you could have something where it's like this combining with this. These two combine and they make a bigger dip. So that also counts as constructive interference. So constructive interference is whenever the two waves combine to make the medium displaced even further from its equilibrium position. Okay. You can also have situations where you have one wave looks like a peak and the other wave looks like a valley. Like that. Okay. And when these combine, well, one has a positive amplitude and the other one has a negative amplitude. So they combine to make a completely flat surface, like an undisturbed surface. And so when this is happening, we call that destructive interference. It is not deconstructive, it is destructive. A lot of times students say deconstructive interference, but that's not correct. And so this is when waves combine to make a smaller wave. Destructive interference can be complete or it can be partial. So in this case, because these two waves have the same size, they cancel each other out exactly, so that we would call that completely destructive interference. But what if the two waves that are hitting each other don't have the same size? Then you get you won't have it cancel out completely. So maybe you have this wave combines with this wave. So the dip, I'll make it more extreme. The dip is bigger than the peak, and so they would combine to reduce the size, and it would just be like a littler dip. Okay, so this is an example of partially destructive interference. All right. So there's the question of how do we perceive constructive and destructive interference. How do we perceive it? Well, it depends on the type of wave. But remember, if it's constructive interference, the displacements get bigger. And if it's constructive, the displacements get smaller. So if we were talking about sound waves, okay, constructive means that it is louder, and destructive means that it is quieter. Okay, if we were talking about one interesting device that uses destructive interference of sound is sound cancellation headphones. So basically what sound cancellation headphones have is they actually are sound cancellation headphones listen to the surroundings. They listen to the sound waves that are coming in your vicinity. And then the sound cancellation headphones then produce or try to produce the opposite wave so that when those two waves superpose, okay, you get nothing. That's how sound cancellation headphones work. It's pretty interesting. So it's kind of counterintuitive to cancel out the sound. You actually make your own sound that is the opposite. Okay, so you kind of make like anti-sound, if you will. Although if you remove the outside sound and you just had the sound cancellation headphone play its sound, it would just sound normal to you. If you have constructive interference of light waves, constructive means that it is brighter. There's a device that relies on the constructive interference of sound waves, and that is a laser. So what a laser is a device that's making a bunch of light waves, and it's making them such that all of the peaks of all of these light waves line up. And so you get massive constructive interference of light waves, and that's why they're so bright. Okay. Laser, in fact, the laser is an acronym that stands for light amplification by stimulated emission of radiation. Believe it or not, it is also possible to produce the same concept but with sound waves. So you have a laser of sound, if you will. With water waves on the surface of the water, constructive is just going to be a greater size wave, right? Rougher seas or whatever you want to call it. All right. So let's do an example of how to. So this is just in general. We're talking about combining waves, but how do we mathematically combine waves? So I'm going to draw a graph here. All right. So maybe we have this wave does this. And this wave goes that. Okay, so here is wave 1. All right, here's wave 2. And let me put some numbers on the axes here. 5, 10, 0. All right. And so what we want to do is we want to draw the total wave, because these waves are overlapping. They're on top of each other. All right. So we want to draw the total wave, because you never, when you look at the surface of the water, you don't see the individual waves. You see the total wave. Okay. And so, yeah, so you don't see the individual identity of the waves. All you're going to see is the total wave. So this is not what you would actually see if this was the surface of the water, for example. You would see the total wave. So that's how we want to draw it. And so the method, you already know how to combine waves. If you've ever been in your math class and you've been given a function f of x, and then you have another function g of x, and you draw the function f of x plus g of x. So it's just like adding functions, okay? Exactly like that, okay? So that's what I'm going to do. I'm going to pick a couple of points along the horizontal axis. I don't even care what the numbers on the horizontal axis are, but I'm going to look at what is the value of wave 1, what is the displacement of wave 1, I should say, what is the displacement of wave 2, and then I'm going to add those two together, and that'll be the displacement of the total wave. So here, both waves have the value 0. 0 plus 0 is 0. At this value, wave 1 has maybe a value of plus 1.5. Wave 2 is minus 1.5. So they add together to make 0. Here, wave 1 has a value of about 4. Wave 2 has a value of about minus 4. So those combine to make 0. Here, wave 1 has a value of, let's say, 5. Wave 2 has a value of still minus 4. So 5 plus minus 4 is 1. Here, wave 1 has a value of 2. Wave 2 has a value of minus 6. 2 plus negative 6 is negative 4. Here, wave 1 has a value of 0. Wave 2 has a value of minus 7. Minus 7 plus 0 is minus 7. Here, wave 1 has a value of minus 3. Wave 2 has a value of minus 8. So the total wave is minus 11. Here, wave 1 has a value of minus 6. Wave 2 has a value of minus 9. So that's going to be like minus 15. That's like down here. And then here they're both 0 again, so they'll combine to 0. So I'm not going to go through the entire. Maybe I'll do one more point. Here we have minus 6 and minus 7, so like minus 13 or so. So now that I have all these dots, I'm going to connect the dots with a smoothish curve. So this is what the total wave is going to look like. So this is what we would actually see, what the surface of the water would look like, if you will. So we notice a couple of things here. All right. Sort of on this side, the two waves are, one is positive and the other one is negative. So kind of on this side of the graph, these two waves are interfering destructively. So this is destructive interference. Okay. On the other side of the graph, we can see that both waves are negative. So they are combining to make a bigger wave. So over here, we have constructive interference. So two waves, they can have, even though they're both separate waves, two waves don't have either constructive or destructive. They can have constructive at one location and destructive at the other. Okay. In fact, right here at position x equals maybe 3.5 or so, right there we have completely destructive interference because they're combining to make a wave that has zero displacement. Okay, so one of the ways that you might be asked to combine waves is graphically. So this is how you do it graphically. I think that you guys understand how to add two functions, f of x and g of x. So anyways, this rule for combining waves is called the principle of superposition. All right. And so basically what it says is that the displacement of the total wave is equal to the displacement of the first wave plus the displacement of the second wave. Okay. Now, oftentimes, so the displacement is a function. So if we look at like this graph, for example, the displacement that the wave has is a function of where I look at the wave. So like over here, wave 1 has a positive displacement. Over here, wave 1 has a negative displacement. So the size of that displacement depends on where you're looking at the wave. So all of these displacements are going to be functions of position. So it's kind of like f of x. But the thing about waves is that waves don't sit still. They wave back and forth, okay? So the displacement is never going to be just a function of position. It's also going to be a function of time, okay? So this is the notation, and you may or may not have encountered this in math before, but if you have, instead of just one variable, you have two variables separated by a comma, this means that the displacement is a function of position and time. Okay? So, all right? So, like oftentimes in physics, in more advanced physics, you have a function of x, y, z, and time. So that's a function of, where you are horizontally, where you are into the page and out of the page, where you are vertically, and when. So that's the notation if you have a function of more than one variable. So let's do an example just practicing that really fast. Suppose that the displacement of a wave as a function of position and time is equal to 4 sine of 3x plus 2t. All right? And for this lesson, this is one of the few lessons in this class where we are going to put our calculator in radians mode. Okay? So in the quiz for today, it's going to ask you, make sure you read the entire text of the quiz. It's going to ask you to put your calculator in radians mode when appropriate. Okay? So now the question is, what is the displacement of this wave at location x equals 1 meter when the time is equal to 3 seconds? All right. So what I'm going to do is I'm going to plug in 1 for x, and I'm going to plug in 3 for t. So I have 4 sine of 3 times 1 plus 2 times 3. All right, so that's 3 plus 6, so that's 9. So the displacement is going to be 4 sine of 9. Remember, that's 9 radians. I always like to put my units in my trig functions just so that it's really obvious. So if we're calculating the sine of a degree, I will put 9 degrees. So that just makes it always unambiguous when you're finding the sine or the cosine of something. You might have noticed that I've done that since the beginning of the school year. Okay, so let me do that. And so the answer is 1.65 meters. So at that location, at that time, that's the displacement. If you wait for a later time, that displacement value is going to change. Similarly, if you move to a different location where you look at the value of the wave, it's going to change. All right. So this is kind of more of an, so we can describe waves in terms of graphs, or we can describe waves algebraically. So describing it algebraically means that you actually have a mathematical formula. Okay. So now let's do another example. At a particular moment, all right, and the reason I have to say at a particular moment is because waves are always changing. Waves don't just stay the same. They have to wiggle. Otherwise, it's not a wave. So at a particular moment, okay, wave 1 has a displacement as a function of position equal to 3 sine of 2x. And wave 2 has a function of position that is minus cosine of 2x. All right. So at that instant, where will these waves have completely destructive interference. Okay? So when I say where will these waves have completely destructive interference, what that means is we're looking for x. What is the x value at which they will have completely destructive interference? And the fact that it says completely destructive interference means that the total wave should have a value of 0 at that location. So I take my d1 of x, which is 3 sine of 2x, and then I add it to my d2, which is minus cosine of 2x. So this is the size of the total wave at position x at a particular moment in time. And I want to set that equal to 0. And that'll give me an equation for x where they completely cancel each other out. So let's try it. So I add cosine to the other side. So I have cosine of 2x equals 3 sine of 2x. I'm going to divide both sides by cosine, and I'm going to divide both sides by 3 as well. So I have sine of 2x divided by cosine of 2x equals 1/3. That is, of course, tangent of 2x. And so I'm going to find the inverse tangent of that. Arctangent, also known as inverse tangent. So now we have 2x equals inverse tangent of 1/3. And then I divide both sides by 2. And so I solve that. Let me solve it on my calculator here really fast. So we have inverse tangent of 1/3 and I get that they will completely destructively interfere at at location x equals 0.16 meters. Excuse me. All right, so next thing I want to talk about, and let me just check if there are any questions because I haven't been looking. No questions. Wonderful. So maybe you guys have seen the graph. If you have the graph of f of x, okay, then you've probably also had the opportunity to graph something like f of the quantity x minus 5. And so how do these two graphs compare to each other? Well, it's the same shape graph, but this one is shifted, okay, 5 units to the right. Okay, so oftentimes what happens is if you have a displacement of a wave as a function of position and time, is you might have it look like this. It might be sine of x minus t. Okay, sine of x minus t. And so what we can see here is t is the shift. So the shift of the graph depends on time. Okay, so the graph, if we look at a displacement versus position graph, as time goes on, it's going to maintain the same shape, but it's going to shift to one side or the other side. And so that is called a traveling wave. Okay, so a traveling wave has a time-dependent shift. So I wanted to show you Desmos, and so we can see how that looks. Okay, I think that's going to go to Desmos. Cool. So, so I have d of x equals 4 sine of x minus t. All right. And so so I have a slider here. So this is displacement versus position. And I have a slider for the time. Okay, so what if we start at time minus 10 and time moves forward? You can see that the shape of the graph is exactly the same, but the amount of shift increases. Okay. If I want to, oh, I can make it a movie. Cool. If I want to, I don't want it to reverse. Just one time. Okay. What if I press it? Okay, cool. Now, what if I make the shift bigger? So now it's maybe 4 sine of x minus 3t. Okay. In this case, the shift increases faster with time. So basically that translates to a wave that's moving faster. What if I change the negative to a positive? Now that's going to be a leftward shift. And so now the wave is moving in the opposite direction. That's pretty cool. We could say, what happens if I add multiple waves together? So maybe I have 3 plus 3 cos. I'm going to make these waves smaller just so that we can see it more easily. Maybe 2 cosine of, let's say, 0.5 x minus t. I've superposed 2 waves, and let's see how it looks. See how when you combine just 2 waves, almost 2 waves looks almost exactly like the surface of the water. It's pretty cool. So what you're seeing is multiple waves superposing, and as they're moving, the superposition changes. If you wanted to, maybe a plus sine of negative 2x plus, or let's say minus t. Okay. I just love how that looks. That's just really fun to me. So anyways, by superposing a couple of waves, we can very quickly produce a displacement versus position that looks pretty realistic when we consider the surface of the water. Okay, so I think that's neato. All right, so that is my lesson for today, and I will see you in the Zoom room.